chambers, TMY Tech products. And we are also open for project collaborations with universities. So for our consultation part, we are ISO 9001 certified, and we work with customers on different problems or design requirements. For example, antenna designs, AMC debugging and analysis. And we are also a certified CST training center, and our training programs are HRDF claimable. So RF stations are the certified technical partners for these various companies. For example, Dassault Systems for CST and Abacus. And then Untitled Lab is for the measurement chamber. And for the RF test equipment, we are the partner of RNS and various other mechanical tools. So for Dassault Systems, they focus a lot on this multi-physics and multi-scale prospect. And for RF station, we focus on these four aspects: structures, thermal, fluids, and electromagnetics. So from here, you can see that within multi-scale, we can go from functional to material for different industries. So for electromagnetics test and measurement, we have the OTA measurement solutions. So on the left is the CATR solutions for 5G, and on the right is the multi-probe system for IoT. And we are also the technical partner for RNS. So for RNS, we are the solution partners where we are able to combine different equipments and supply it as a total solutions. For consultations, we target different industries, for example, high-tech industries, automotive industries. And within different industries, there are different problems. So we will be engaging with the customers to discuss on different problems statements. For example, signal integrity, power integrity, or radiated emissions problems, or some EMC-related problems. So these are some of the solutions that we provide. Right. Back to the title of today, which is designing, testing, measuring a 5G millimeter wave phase array. So we all know how to design, how to test, and how to measure. But what is a proper workflow where we can combine everything together so that the workflow itself is very streamlined? So in today's talk, we'll be looking at, firstly, how to design a simple small cell array. Next, we'll be looking at the evaluation of a millimeter wave antenna quality. Then we'll be looking at how to control the millimeter wave phase array and measuring the antenna and devices. And finally, we'll be looking at some case study, application case studies. Right. So we know that right now, connectivity is the key. And communications, wireless communications, everything, there will be a need for antennas and communications. And right now, everyone is talking about 5G. So we know that 5Gs have these three key elements, which is massive connectivity, low latency with ultra reliable, and enhanced mobile broadband. And how we can achieve this is by having antenna arrays. So for this example, we'll be looking at a simple sub-6 GHz 5G network where the array working in a suburban coverage, it is more towards like a horizontal beam steering. Whereas for urban coverage, there will be a lot more multi-path, and the beam steering will need to be in horizontal and also vertical. Right. For designing an antenna array, there are a lot of different aspects. For example, the size aspect, maybe a dimension of not more than 40 centimeters. And sometimes during the design, the requirement will be not too big, not too heavy, because we need to hang it on a tower, and it cannot be too expensive. And of course, it has to be flexible and robust. So in this example, we have a 8 by 8 element array, taking out the 4 elements at the corners. There will be 60 elements, and we separate them into 4 quadrants so that we can control the beam at 4 different directions. So during the designing phase, we'll be looking at the antenna design of a single element. Then we'll be looking at the array design. And after completing the array, we'll evaluate the installed performance where we hang it on an antenna mast, for example. And finally, we will do a coverage evaluation. So firstly, the individual antenna element designs. So how do we kickstart with this process? Is that first, we have the requirement specifications. What is the frequency range? How big of the array elements will be? Do I need to have a single polarization or dual polarizations? Those are the requirements. And the easy way of getting the antenna is by using antenna muggers, where there is a huge library, hundreds of antenna templates. Everything is parameterizable, so you don't need to design from scratch. So basically, you just key in the requirements. For example, the frequency range, you want to scan to how many angles. And from there, you can choose the specific candidates. So in this case, there are 3 or 4 candidates, and we can export this immediately to CST. So in CST, we can simulate it by a standalone or a unit cell simulations. In this example, we can see there are 3 different candidates, and each have different behavior. And these simple simulations can be done directly inside antenna muggers. And once we have a few candidates in mind, we can export them into CST and run a detailed simulation with better mesh. If we are using frequency domain of the CST Studio Suite, we are able to simulate it using antenna array tasks. So for antenna array tasks, we can simulate it by using unit cell and also full array. Everything will combine together, making it a very streamlined workflow. For unit cell simulations, we'll be looking at the active element pattern, which this post-processing template is already predefined during the antenna muggers exporting. So for this antenna design 1, the first candidate, the evaluation of this candidate is by looking at the antenna element pattern, the AEP, at different spacing. So on the top is 40 millimeter, and at the bottom is 50 millimeter. So this plot here is a UV plane plot, and the center is the ball side. And we can see that based on different scan angle, the red color means that the performance is good, whereas yellow or green color means that the performance is not good at larger scan angle. For the next antenna design, the third candidate, we can see that the performance is not so great, even for 40 or 50 millimeter spacing. So from here, this very simple simulation can help us quickly evaluate which candidate of the antenna, if we assume it as an infinite array, which is more suitable for our use case. For example, we want to scan for plus minus 45 degree. So once we have the candidate, using the array task, we can immediately convert it into a full array antenna design. So for commercial case, normally there will be a housing already. So the housing may come from the mechanical team or customers. And it is incredibly easy. You just need to import the step file or any 3D generic files, and we just import into CST. Whereas for the antenna unit cell element, we just use this array task to create the full array XY plot. So when we have the full array, how can we simulate it very efficiently? Do take note that for this housing, the surrounding is a metal. So the surrounding will have effect to the antenna array. So firstly, we can simultaneously excite. That means we excite every port together with a certain amplitude of phase based on our excitation list. Secondly, we can simulate sequentially. That means port by port we simulate. And then by using post-processing, we combine the individual far fields to give it a specific phase and amplitude to give our final beam radiation pattern. So the sequential method is a lot more efficient because we can do the post-processing very easily. However, if we have 60 elements, that means we need to run 60 times. And for this approach, when the array gets larger, if we have hundreds or thousands of antenna array, that simulation method becomes not efficient anymore. So we have this simulation by zones method, where we take the few elements that are in a similar geometry. That means it has a very similar geometry based on the surrounding neighbors. For example, you can see the top row has a similar neighbor, which at the bottom is antenna patterns, and at the top is the housing. So in this case, we can simulate them by zone, and in this case, 5 zones separately, and we just copy-paste the results to all other elements. When I say copy-paste, it means that this simulation by zones method will do that automatically. So is it everything the same? So here we can see at the bottom left corner, there are 5 elements. The radiation pattern of each element are shown in the middle. And you can see they look quite similar, but not quite similar at the same time, because the surrounding is different. For antenna 1 and antenna 4, for example, the top and the right, there are some neighbors, but the others don't have. So the radiation pattern of each element will be different, but how big of a difference it will give? So you can see here in one quadrant, all the elements looks a bit similar, but at the same time, there are differences. So now the challenge is how do we zone them so that we can get efficient simulation and at the same time accurate enough. So when we say very efficient, that means how much we can reduce the total number of simulations. So these are some examples of zoning them. You can see in the video here, the antenna arrays are zoned according to locations. So this is one of the zoning method, and the guideline for zoning is to maximize on the accuracy. So you can see this is one of the zoning method, and shown now is the second method of zoning, where we have individual zone for the corners, and then the center will be zoned as one single zones. This way we can reduce the simulation time and at the same time getting higher accuracy. So for this, how to do the zoning, each designers will need to think based on their own design perspective. For example, the polarizations of the requirement, how is the array layout, whether it is a symmetry layout or a non-symmetry layouts. So here we are comparing 4 different zoning methods. The first one, we have 5 zones, which reduce the total simulation time to just 10%. And then zone method number 2, 3, and 4. For the 4th zone method, which gives us the highest accuracy, we split into 32 zones and reduce the simulation time to 50%. Looking at the radiation pattern, this is the baseline where we simulate each and every antenna elements sequentially, that means one by one. And then we have the other zones results. And finally, if using the 32 zone, which is supposed to be the highest accuracy, we can see that the result is very, very similar. Even the main beam, the front loop, and the first few side loops can capture the results very nicely. And do take note that the side loops or the back loops and the front loops, there is about 30 to 40 dB difference. So the approximation is considered good enough. So depending on your requirement, you may use the 5 zone method or even the 32 zones method. What about shifting the angle to 45 degrees? So we can see that based on the baseline method and the zone set 4 method, the radiation pattern is still very close. This approach is extremely useful when we have a large array. So for example, this is a 429 element array, and we can just simulate it by using 5 or 9 different zones. And we can get a very good correlations between a full array and a zoning method arrays. So once we have obtained the individual radiation patterns, we can then use different excitation for different amplitude and different phase. So here we have 4 different quadrants, and we can excite them individually. And we can see the approximation based on antenna markers and CST is very close to each other. And finally, we can simulate different kind of combination of amplitude and phase, and then post-process the far field to get what you are seeing here. Basically, we are seeing that the radiation pattern, we are splitting from 1 to 4, and then to 4 different directions, and combine them back to 1. So all these simulations are done purely by post-processing. So we don't need to rerun the simulations again and again, which will take hours or days. So next, we always will need to simulate the antenna arrays when it is installed onto a certain items, be it car or a building or a ship. So when we install them, we will need to simulate both the antenna and the environment. So in this case, we will use bidirectional hybrid simulations to simulate the coupling behavior between antenna array and the environment. So for these simulations, the first method is to simulate all ports, and then we can get the full coupling matrix, which is the S parameter of both Tx and Rx. And then the second method is to simulate simultaneously, where we can get the coupling parameters, the F parameters, and obtain the radiation efficiencies. And once we got that, we can also simulate the behavior of a Rx, where we have different Tx at a location, for example, installed on the buildings. And we can simulate the received power if a user is walking past the street. So you can see here, the beam is changing the direction based on the user's locations. And you can see that the green lines on the right is changing from Tx1 and exchange to Tx2. So orange line is Tx1 and the gray line is Tx2. And you can see the handover from Tx1 to Tx2 based on the location of the users. So this is a very clear example where we simulate from the design stage all the way until the implementation stage. So next, how do we evaluate millimeter wave quality? Can we change or can we obtain a single unit for a millimeter wave antenna? So the unit that we normally use is CDF. In this case, for this millimeter wave phase array, the CDF we want to obtain is this cumulative distribution function. So for this CDF, the requirement is around 11 at 50%. So the meaning of this CDF is that 50% of the total sphere is covered by EIRP more than 10.5 dBm. We will use individual angle and combine all the angles to get the total EIRP pattern. And based on the pattern, we can calculate the CDF. So here you can see 3GPP specification defines that at different band, the CDF at 50%, we will need different values, for example, 11.5. To obtain that, we will first get the radiation pattern beams of different angles, and then we combine them to get the total EIRP pattern. So in the next slide, you will see 5 different beams combining into one, and this is the total EIRP that we obtain. And based on this total coverage, we will be able to extract the CDF at 50%. So over here, we can see that the CDF at 50% is 10 dBm. So this is below the requirement. How can we improve this? So we can improve this by adding another array at the other side of the phone. And this will give us CDF 50%, and the EIRP will give us 15 dBm. So just by adding another array at a different angle, then we can have a wider coverage. So these are some of the aspects when we are designing millimeter wave antenna. So the CDF values we can evaluate based on different combinations of antenna directions or antenna selections. We can also change the material of the device, maybe changing it from glass to plastic or to metal mesh or etc. So at the end, the objective is to obtain a good enough CDF value at a minimum cost or minimum antennas selections. So next is human exposure certification. For sub 6 GHz, we normally look at SAR. But for millimeter wave, the penetration into human body is so low that it cannot penetrate into the human body. So to counter this, we can use power flow in planes around the device. So if you use power flow, we'll be able to get the field magnitude at a certain distance. So this is what we are more familiar to, the SAR, specific absorption rate, for sub 6 GHz. So you can see that the penetration into human body is much higher. So in CST, we have the SAM Phantom, which is pre-installed when you install your CST. And also we have this hand gripping Phantom as well, where we can place the hand at a specific angle to hold onto your device. So this is the simulation for SAR, and from that, we can obtain what is the point SAR or what is the 10 gram SAR values. So for 28 gigahertz, since the wavelength is so small and the human body is so big, do we need to model the human body? So right now, for this 38 gigahertz or millimeter wave scenario, we normally do not model the inside of the human body. We just need to model the human body as a PEC, perfect electric conductor, and apply a thin sheet of human body material to mimic the reflection from the human body. So we can import the human design directly from 3DX, or even if you have voxel model, then you can import them. And you can also position your human body based on a specific pose. So similarly, to simulate a mobile phone together with a human body, we don't simulate the whole thing in one go. That is the brute force method. That is not efficient at all. So what we can do is we simulate the device with the hand in a high accuracy simulations. Then we obtain the near field and we use another solver, be it integral solver or asymptotic solver, to simulate the environment, which is the human body holding the phone. So this hybrid workflow is more efficient and it can give us higher accuracy. So you may ask, do I need to simulate the phone together with the hand and human body? So the answer is yes, because you can see there will be small changes to the radiation pattern based on the environment. So you can see the changes from just the hand and the user have quite a big impact to the radiation pattern. We can also simulate the hand placement, and based on different hand placement, we can get whether it is blocking the main beam or not. So in this example, we can see that it is blocking, but it's not very significant. We can still have a main beam pointing at the direction that we want. So this antenna array should still work. So finally, on the compliance regulations for millimeter wave or FR2, this is the requirement where we measure the power flow at a 2 centimeter distance on a plane of 30 centimeters. So once we got this, we can simulate the devices with high accuracy, and then we obtain the near field and export the near field into another solvers by using the hybrid solvers to calculate the planes. And based on the planes, we will be able to get the power flow at a certain distance. And this will be the so-called compliance regulations for FR2. So we have gone through how to design and how to evaluate our antenna. So right now, how can we do some controlling? So RF Station, we partner with TMI Tech, and we have this 5G millimeter wave developer kit where we can control the phase angle, the phase, and also the amplitude. We all know that for beam steering, we need to change the phase and also the amplitude to control the direction of the beam. We can change the gain to improve the side lobes. And ultimately, we want to change the directions. So here you can see a simulated beam on a 28 gigahertz phase array. We change the phase and then we obtain the final radiation pattern. I will play a video for this 5G millimeter wave developer kit.
Beamforming is a key technology that enables 5G or beyond 5G high-speed communication across a wide range of industry and applications. We are excited to support 5G mmWave development with our developer kit, which is cost-effective, ready to use, flexible utility, and capable of opening up new markets throughout the world. The kit includes everything you need to get started with mmWave innovation, from a 5G FR2 beamformer to 40 GHz RF cable. mmWave Developer Kit is the best choice to start the mmWave innovation journey. Developer Kit has 3 key benefits. More than 8 pieces of high-frequency components with affordable price. Comprehensive toolkit include a 5G FR2 beamformer, array antenna, COCO antenna, continuous wave source, power detector, RF cables, power combiner, amplifier. The RF components that are not easy to access are all provided. It is noteworthy that B-board can do 2-dimensional beam scan and control by GUI. Software and hardware all in one. The intuitive GUI Tmx Lab Kit is our in-house designed software interface GUI. By connecting to the B-board via LAN port to control the phase and amplitude of each RF port to form the beams. An API is included, and it is compatible with LabVIEW, MATLAB, Python, C#, C++, and other programming language. A versatile 5G mmWave courseware and lab cookbook included. The lab sheet leads professor an easy life in courseware preparation, enabling engineering students to learn the fundamentals of beamforming and mmWave propagation. Allow engineering students to set up various experiments. By observing beamforming results on instrument, students can understand array antenna, link budget, constructive and destructive interferes. Familiarize with mmWave RF front-end, or even verify the theory about phase array. Detachable antenna design. It provides antenna swapping flexibility for array antenna verification by docking the antenna to a beamformer via K-connectors. K-connectors and RF cables make the connection between components flexible. Various setup can be carried out based on different mmWave deployment scenarios. Fields include RF engineering, antenna design, protocol development, arrays and validation, and more.
All right. So we now see that we have a device that we can control the antenna elements. So we will be able to control the phase, and at the same time, we can control the amplitude. We can now measure the DUT, or the phase array that we design. So in this case, to design the millimeter wave phase array, we'll need to use some different equipments. So firstly, the anechoic chambers. At millimeter wave, the standard chambers no longer valid. We need to replace the feed horn to a CATR, compact antenna test range. So this CATR method is by using a reflector to reflect the wave from the feed horn to give us a plane wave. So why do we need CATR? We all know that to obtain far field, we need the distance of 2d squared over lambda. And we also need a plane wave for measurement. So this is especially useful for radiation pattern measurement, where we want to have a stable plane wave without doing some near field to far field conversions. So based on these requirements, we can now calculate that for a DUT of 40 centimeters, we will require 42 meters to achieve the far field at 40 gig. So it will become almost impossible when we are at such far distance because the attenuation at this frequency is huge. So we will need CATR. Next, we will be using the VNA. So in this case, we have the ZNB40 series, which is a 40 gigahertz VNA. And if you do not have the facility to obtain a 40 gigahertz VNA, we can use the up-down converter from TMYTech to up-convert the signal from a sub 6 gigahertz device. So these are some of the use cases where we can combine the use of UDBox with VNA or software-defined radio, SDR, or we can even use it together with SG and SA, signal generator and spectrum analyzers. So this is a video taken in our office where we set up a simplified version of CATR solution in our office. We can also customize the solution based on different requirements, the size, quiet zone, the sensitivity of the results, and so on. So this is also a video, so I'll just play it. Hello everyone, RF Station would like to present our 5G millimeter wave phase array measurement solution. In this video, we will be measuring the radiation pattern of a millimeter wave phase array. So this is how the complete setup looks like. Let's go through the setup of individual equipment. First of all, we have the compact antenna test range, also known as CATR. Then we have the RNS ZNB series VNA. We are using the ZNB8 series to showcase the dual channel UDBox 5G, which is an up-down converter. Then we have the turntable, which is part of the CATR system. The DUT is the B-board connecting to a 4x4 phase array. Then we look into the CATR system where it consists of a detector and a feed horn. Our feed horn can support from 26.5 GHz to 40 GHz. To control the B-board and the UDBox 5G, we use Tmx Lab Kit Software where it provides the GUI to easily configure the devices. Here you can see both B-board and UDBox are in the same GUI. The B-board is set in TX mode and all 4 channels are turned on. Then the UDBox is configured by setting the desired RF frequency at 28 GHz and the IF frequency at 5 GHz. The LO frequency will be automatically configured based on the RF and IF frequency. By now, everything is ready and the measurement can begin. We are using Etherlab's Maxwell to control the turntable while capturing the data from the VNA. Shown here is a 2D turntable, which only gives us single-axis measurement. We can also upgrade the turntable to a 3D dual-axis turntable, which will give us 3D radiation pattern measurement. Within the Maxwell GUI, we can see the measurement data being recorded in real time. To view the results, we just need to load the measured data file into the Maxwell viewer. The Maxwell viewer is an easy-to-use GUI to visualize and analyze the 2D or 3D measured data. Here, we are looking at the measured radiation pattern of the millimeter wave phase array. Next, we beam steer the phase array from 0 degree to 30 degree by controlling the 4 individual phase steps on the B-board. And as you can see, we successfully steer the main beam from 0 degree to 30 degree. That's all for now. Do contact us to find out more about our CATR measurement solution. Thank you. All right. So, sorry. Let me just reshare my screen. Right. So we already see how we can measure the radiation pattern. We can do this by measuring the radiation pattern or by doing other use cases, for example, active measurements or passive measurements. So right now, I will show you some applications where we are using a HD video streaming to stream from TX to RX. We are using a software-defined radio, SDR. In this example, it is using a USRP from NI. And it is also a video where we see how from the TX radiate to the RX. And at the same time, we will be looking at the constellation chart, the throughput, and etc.
This is a development system for mmWave prototype. Can be using high-definition video streaming, beam tracking algorithm, and channel sampling prototype. The solution demonstrated here is composed of developer kit, UDBox 5G, and USRP. Let's have a look at how it works. The signal from USRP is being upconverted to mmWave by Tmx UDBox 5G. It will then transmit signals from the beatboard to the COCO antenna. Here's a quick overview of its product. Beatboard, a beamformer with an array antenna from the developer kit. It has 4 RF channels that can be controlled individually via a software GUI. COCO antenna. It can perform omnidirectional radiation at a vertical plane. UDBox, an op-amp converter that can upgrade the intermediate frequency to a higher frequency. The frequency range is from 24 to 44 GHz, and it fully supports the mmWave bandwidth. Tmx Lab Kit is a software GUI for UDBox and beatboard. It is developed in-house by Tmx. Let's begin with UDBox. Let's say we'd like to upgrade to 28 GHz, which is the RF frequency. The signal from USRP is 2 GHz, so set the RF to 2000. It has an internal local oscillator, which is OCXO, and it's very stable. No internal reference is needed. Move on to beatboard. The transmitter side and receiver side can be easily switched. You can adjust the stepping of each channel as well. Back to the solution. Align the beatboard and COCO antenna so they are pointed directly at each other. From the video and constellation diagram, we can see that signal transmission is clear and stable. Right now, it is at 0 degrees. Try to steer the beam to 30 degrees. We have already calculated the phase step. It is 0, 15, 30, and 45. The video stops and the performance drops. Turn the beatboard physically to 30 degrees. And the signal is able to transmit again. And the stream continues. Just want to clarify, this is a real-time demo. If there are obstructions in between, the video freezes. With this solution, you can easily validate your beam tracking algorithm or conduct channel modeling or other signal processing studies.
Right. So you can see that for actual applications, we can still use the same equipment to configure the beam that we want. We can also use the API to control, for example, the beam by using your own algorithm, or do some beam tracking algorithm optimizations, or any various designs. So not only we just design and simulate the antennas, but we can actually use the antenna for actual applications. So you may design your antenna, and then you just need to swap with different antennas, normalizing your results and see whether the performance is improved or worsened based on your controlled designs. So to close the session, we have learned that how we can design the single elements up to array, up to the install performance. And then we also know how to evaluate the design based on CDF and also the power flow at a certain distance. And we also know how to control your designs based on changing the phase and the gains. And finally, to measure your antennas by looking at the radiation patterns, by checking if your beams steer to a certain degree based on different excitation inputs. And finally, we look at the actual applications, which is a HD video streaming. So for this case, we are using a HD video streaming because the USRP can only support up to HD. So if you want to do a 4K video streaming, you will just need to upgrade to a higher spec software-defined radio. Then you will be able to do that. So to conclude, we already designed the antennas, everything, but we have not looked at the mechanical aspect. So it has been increasingly popular to simulate not only the antenna, but the whole package together. So in this case, we may also look at the signal integrity based on the different PCB designs. We can also look at the heat transfer and cooling because for these high power, high frequency devices, it is always very sensitive to temperatures. And the heat generated is also very high. So we can look at how we can efficiently cool down our devices by running some thermal simulations or even some mechanical simulations based on the thermal stress. Because we know that once a PCB is having a high temperature, it will start to expand and the design will start to change. And based on that, we can see the actual mechanical deformation in the simulation as well. So that's all for now. Thank you.
All right, thank you, Dr. Ding, for the presentations. We already have one question. Dr. Azrami already raised his hand. So now, can we open the floor for the Q&A session?
Yep.
Dr. Ding? All right.
Yep. Let's flow the questions. I'll try to answer the best as I can.
Hello, Dr. Ding. Thank you very much for your nice presentation.
Thank you.
Yeah, I've been following from the beginning, and then it was a very interesting talk. Anyway, I'm interested in the in the hybrid simulation that you highlighted just now about the simulating the both user and also antennas, right? Is there any possibility that if the human is moving, right? Because you probably need to simulate every step of the user moving around or try to sit down on chairs and things like that. Is it possible? Because because we know that probably 5G or 6G has to be, I mean, in mobile propagation thing. So
yeah.
Are you trying to consider that, or probably in future how to integrate those simulation with other like ray tracing simulator, things like that? Yeah, that's my question.
Yeah, thanks. So from the hybrid simulation just now, we know that we can import a posable human. So you bring up a very good point. So once we have a posable human, we can change the human posing geometry, whether sitting up or standing up. Then we just need to run a few simulations. So as we know, the simulations is a passive simulations where we can't do a transient kind of movement, but we can do a step-by-step. So for example, the first step, then we run the simulation and we obtain the far field. And based on that far field, we can import the far field into another environment by using SPR, which is the A solver. We use the A solver to simulate the ray at a specific environment. maybe in a city where we have different TX. And you can do these hybrid simulations by interchanging the positions and then go back to the environment and then change the position again and then go back to the environment again. So we can do that quite efficiently by having a standard workflow. So for example, we first have the antenna, and then the next we have the antenna with a human body, and then we have the environment. So by doing a loop in the simulations, we'll be able to see the changes based on different positions of human body.
You mean that can be done in even in CST, yeah?
Yes.
Okay.
In CST, we need to create the task, and based on the task, we just need to do a hybrid simulation, whether it is a bidirectional or a unidirectional simulations.
Okay, thanks. Thanks.
Yeah.
All right. Thank you, Dr. Azrami, for the questions. Dr. Ding, do we need to add like Simula software in the CST or?
Okay. The Simula is actually the umbrella under Dassault, where it has a lot of different simulation tools. So within CST itself, we already have the antenna markers, the hybrid simulations and everything. It's just that if you want additional things, like for example, a different kind of human body or a different kind of object that you want to import from another team, maybe the mechanical team, then the 3D experience will be a useful tool to share among the models. But within CST itself, we are already able to use the posable humans, the human body model, the phantom models. All those are already in the CST package.
In one of your slides, you said that we can import the casing, right?
Yep.
Can we change the materials? For example, I would like to import pot. So we have Teflon, and we also have the copper. Can we like do because it comes in one file? Can we change the materials for different?
Okay. So different files will have different challenges. So if the file is a single object, like when you import it is just one item, you can't separate them into like 5 or 10 different components. Then it is quite difficult. We will need to do some slicing, some healing to make it into different parts. Then we just assign the material individually. So yeah, but for CST, when we import, like for example, step file, it doesn't have the material information. We need to assign it manually. But if you import something like a SolidWorks file or CATIA file, then sometimes the material definition is already predefined inside. Then you do not need to do anything else.
Okay.
Yeah.
Right. Any more questions from others members? For our participants, yes, we have one. Mr. Hammond, please.
Yes, thanks a lot for the presentation, Doctor. I have basically 2 questions. One question is, what if we don't have megas installed? Then what will be the process from? Is about the measurement. How do you validate the results you got? You compare it to what? To the simulated results or not? And there is another concern about the CATR chamber. Is the environment, the shield is metal or it is wood or what? How does it make difference? I mean, for the radiation pattern. Thanks a lot.
Yeah. All right. So let's look at the first questions. If you don't have antenna markers, how do you validate your designs? So if you don't have antenna markers, basically you need to start from scratch. You need to design your antennas, and basically that is your designing stage. You may have theoretical values, and based on that theoretical values, you can only validate your simulation results. But of course, within simulations, you can use different solvers like, for example, frequency domain or time domain or integral solvers to validate your designs, because ultimately different solvers is totally different algorithm. And if different algorithm gives you the same answer, that means that geometry is behaving like how you intended it to be. But given that your model and your fabrication prototype is the same, so there are a lot of cases, like, for example, in simulations, you do not have a feeding network. So you can't expect the performance to be identical to your prototype where you have a feeding network. So that is how you need to simulate and check your designs. And for the second questions on regarding the environment impact on CATR, as you can see in our office, we do not have a big chambers. It is a simplified version of a CATR. It works, but of course, there may be environment interference. Maybe when the door is open or closed, there might be some reflections. So it is always best to do it in a shielded environment where you are shielded from the external interference and you have all the absorbers covered. So there will be slight interference in the measurement. We do notice some small changes in the results when I'm standing beside or when I'm standing behind the measurement DUT. But ultimately, it depends on your requirement, whether or not that small difference is going to impact your findings. But otherwise, yeah, we need to balance out the effect. Did I answer your question, Mr. Hemin?
Yes, thanks a lot.
All right, thank you.
All right, thank you. Let me check the chat box. No questions. So any other question from any other participants? So don't forget to sign up for the attendance for today. I already attached the link at the chat area. Okay, we will send the recorded version as well as this e-certificate. Any question?
Oh.
Let's check.
Please don't feel shy.
Yes, please don't be shy. Okay, this is the time for you to ask any question.
It is just sharing, so we learn from each other.
Yes. Let's check. I saw Chat Mohammed Noor here. Perhaps you want to ask a question. I think Ding quite familiar with CM Noor.
Yeah.
Hi.
Yes.
I think for today I have no question.
You can ask me any question also.
He has a question about Untitled Lab.
The one we can talk in details together.
Different webinar, different meeting.
Yeah.
Is there any more questions? Perhaps that I think that's soalan. If no, perhaps we can take a group photo before we end the session. Can we do that, everyone? Check. Yeah, Dr. Jim already turned on his camera. He's already ready. All right, let me change the layout for this computer. Tiles, okay, all right. Okay, now I can see everybody's face. Okay, since there is no more questions, so now it's a photo session. So everyone say peace. Okay, ready? 1, 2, 3. All right. Thank you, everyone. Thank you for joining us. And thank you again to Dr. Ding for your time sharing with us the sharing session. Hope we can see you again in our next webinar. And thank you everyone for joining us today.
Thank you, Dr. Sai. Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Thanks, Ding. Thanks.
Thank you. Bye-bye.